Welcome to the 22nd lecture in mathematical finance. So today we will finally solve the portfolio optimization problem in an incomplete market, so potentially incomplete market, because it does not exclude the case of an incomplete one. But for the complete market, we already had some easier method to solve the portfolio optimization problem. So let me recall what we wanted to do. So we have, as usual, given some initial capital denoted by x0, and we assume that it's positive. And we have a utility function. Here, for simplicity, we assume that it's from maps from R to R. Utility function. Then we wanted to study the optimization problem, which was telling me it was usually denoted by P. So we wanted to maximize the expected utility of our terminal wealth if allowed to maximize over all these investment policies, which we have defined last time, such that we have the linear constraint here that at time 0, we are only allowed to invest what the money we have. So the initial capital x0. So here as last time, the maximum, and of course we have to show again that this is maximum is actually a maximum, not only a supremum, but this will be done today for all investment strategy policies. And what we want to keep in mind is that we have here the Markovian structure as an extra assumption on our underlying market in the sense that the discounted returns of the risky asset are independent. So basically we can always make our investment decision just based on the capital we have at the current time. So the idea to solve it, this is what we developed today, is the so-called the dynamic programming principle. So what was it? I mean, we discussed it also already last time. So the idea is that instead, I mean, here we have a underlying financial market with T time steps, T trading periods. And in each of these trading periods, I mean, we want to decide how to invest. So this is somehow a global optimization problem. And the dynamic programming principle tells us, okay, so let's solve always the one-step optimization problem. So we solve at each step a maximization problem, maximizing basically our gains in this trading strategy, in this period. And then taking all these local optimal trading strategy together, we get the global optimal trading strategy. And this is here possible because we have a Markovian underlying structure. So meaning the discounted returns here are independent, right? So this is why we really need the assumption. But I want to emphasize this idea here. I mean, this is a very central idea in many optimization problems. So depending on what courses you will take in the future, you might see this idea popping up in optimization problems and in different other areas. So in order to capture this idea, we introduce the function j, or to implement this idea. So jt is that the terminal time is just our utility function, and at time t, well, it's the supremum of all investment policies, and now maximizing the terminal, also the expected utility our terminal wealth creates if we start trading at time t with the capital X. So this is, I think, where we finished last time. So remark. So JT stands, this is the definition, for the maximal expected utility of the terminal wealth capital if we start at time t with the capital X, right? So this is the idea, and the mathematical formulation is this JTX, right, defined. Okay, so now let me present you the idea of this dynamic programming principle and how we get a solution to this optimization problem P in our underlying market. This is the context of the theorem for this section. So this is 617 in the lecture notes. So suppose T is a finite and arbitrage free. And this is what we always have to assume. Otherwise, we already understood that if the market is not arbitrage free, this optimization problem is degenerated. So there exists no proper solution. And the returns here, this is the standing assumption of our section. So the returns are neutral. But the main point here is that this, if you have seen it, isn't that the underlying market becomes a Markov process. And we just make a stronger assumption here in order to not necessarily to talk about Markov processes. All right. So what is now the statement of the theorem. So first, okay, this is rather trivial. So JT at the terminal time is just given by the utility function, right? This is true by definition. So this was the easy part to prove. The harder part is actually to prove this recursion formula. So if you want to have JTX, so the maximal expected utility of the terminal wealth if you start trading at time t with the capital X, well, it's actually enough to consider a decision rule, so the function f, which has to be, of course, measurable function, so from R to D. So these are the D position in the risky assets. And then you just maximize over the T trading period, T plus 1 trading period, the function JT plus 1, which takes as an input the, well, so this is, so this is the wealth at time T plus 1 if you follow F, and we write down here our standard recursion formula. So this is just determined by our decision rule and then the returns, the discounted returns in this trading period. And now, and so you see, okay, the terminal time, well, if you start at the terminal time trading with the capital X, I mean, there's no period trading going on anymore. So the expected utility is just your utility of the amount you have, the terminal time. And here you start at time t and you want just to maximize over the next period. So over the period t plus 1. And your new target function is just the JT plus 1, right? This is the guide. So what you can do in the end, morally, let me write, yeah. So let me write the theorem and then I comment a bit more on this. So what is, of course, we also want to have, furthermore, there exists an optimal investment policy P star consisting of starting at 0, sorry, for P. That is, so just to recall what optimal investment strategy, investment policy was. So this is, if I follow this investment policy P star, my expected utility of my terminal wealth generated by P star is equal to the maximum of all investment policies, maximizing here over the expected utility of all these investment policy. Okay. All right. So what was here? Great. So what is the picture here? We started time 0 up to time t. So this is our timeline. So this is time 1, time 2, time 3. So this is the terminal time 3. So what is telling me, okay, at the terminal time, depending on what capital I have, my expected utility will be just u of x. Right? So this is easy to solve. Okay, so we want to have the biggest possible x here. And what we do now is we go back one step and then, well, okay, what does this mean here? So my J2 is equal to the supremum over f. And now here, this is just the utility function. And then I have here my decision rule of f. Right. So at time 2, this is the second last time. So I maximize just over this period, which is telling me this I have to do. And now I'm going back a step again and say, well, at time 1, I want to maximize again over all decision rules I can take at this time, but now I plug in f2 because as my new target function, right? And so on. Right, so you basically can use the backward induction idea to go backward, and you see what you have to optimize in each period. And then you only maximize the target function over the next trading period. Okay, and this picture is basically also the idea how to do it. I'll also prove it. So let me do the proof here. So first thing we wanted to do here, as in the picture, we consider J t minus 1, which is just, well, my possible decision rules. And then I maximize the utility, so the expected utility over the terminal wealth I can generate it if I have the capital X. So this means this is a t. And this is the capital I assume to have at time t, capital T minus 1. And then I split based on my decision rule, my capital. I invested this into the de-risky assets. So my discounted, I have to multiply it with the discounted returns. And right. So this is the first thing I want to maximize in this theory. But now, note. This is a portfolio optimization problem. In one period, right? Because if I start at time capital T minus 1, I just have one trading period left. So actually, we know how to solve this. So this is what we have learned. I mean, what we have solved on Tuesday. Okay, so we can solve this. To exist an optimal f star, and since we are at time t minus 1, so we label this f star with t minus 1 for bookkeeping reasons. And this is, if you want to look it up, what we have seen in proposition 6.13. Okay. So let's keep going backwards. And here, make it green. We make the following observation. J t minus 1 is again strictly increasing, strictly concave, and bounded from above. So what way? So this is, of course, I mean, this is something one needs to observe and understand and do. And this is actually not simple. So it's actually a hard point to prove. So we will, I mean, here, I mean, I think this is a technical point and I don't want to spend a lecture on proving it. So let me here just give it to you as a fact that if you have utility function, which is bounded from above, and you plug it in this JT, then you get again a utility function, which is bounded from above. Right. So why is this good for us? Because this means we are facing again a utility maximization, which we can iteratively solve. We stick to blue. And we can iteratively solve one period portfolio optimization problems to obtain, and this is again our proposition 6.13, vectors, or basically an investment rule which optimize these local optimization problems we have. So this is P star. Okay, so if we go back, I mean, this is actually somewhat the second part, which we haven't proved yet, but the second statement means here, so there exists an optimal investment policy P star, which has this property. And actually, if this iteration formula here is true, then the P star we found is actually the optimal solution, because then we can just like iterate this formula to see that this P star we just derived has this property here. But for this, we first need to prove this recursion formula. All right, so let's prove this recursion formula. Okay, how do we do it? Let me introduce the following set M. So this, which is the set of function from R to R, which are strictly increasing, strictly concave, and bounded. And bounded from above. Okay. So this is basically the class of utility function. We can plug in our optimization problem, and then we're able to solve it. So this is the function, the set of JTs or utility function that we care about. And now we want to also have two operators. So the first one is T, which takes such an utility function which is bounded from above as an input, and then spits you out a utility function which is bounded from above. No. Right. So this T is, so what this is the operator. So the operator is defined as follows. I mean, you won't be surprised to see it now. This is just our JT if we start with the capital X at time t. So here we have V. V stands for general utility function. You have your recursion formula, which gives you the capital at time t plus 1 if you start at time t with the capital X, and then you take your decision rule F in order to invest in the market, and the returns are in this period are given by R tilde t plus 1. Right. And now what the second operator is actually this corresponds to the JT. So here it does not like depend on a specific decision rule anymore. Because we take here the supremum of all decision rules. And then we want to maximize, of course, this expected value here. So in terms of the operator FTV, the supremum was just given here by taking the supremum of all decision rules and then maximizing the operator T, small t, F. Okay. Okay, so these are the operator, like abstractly speaking, corresponding to our JT. And here again, make it in green. I mean, this is the same. We again make the observation as a fact that JT really maps utility function which is bound from above to a utility function bound from above, right? This is the same technical point we already dropped it once, so we can also drop it twice. Okay, so this is okay, and now we basically want to do a backward induction because, well, first thing we know is by definition JT equals to U. This is, if you go back to our theorem, well, the first thing we claimed, so JT at the terminal time is just the utility function. Okay, that was easy because this is just the definition of JT. So we want to use the backward induction. Let me write this. Down for you, backward induction. We want to show that so there's actually two equations we want to show. So first, the expected terminal, the expected utility of our terminal valve of J star. So this is the P star. This is the P star we just showed that it exists, or we just define, given that this P star starts with the capital X at time t is equal to our operator JT of FT, so TT, so that's what I wanted to say, of JT plus 1 X. And then here we have JTX, as I already said. Okay, and well, for later reference, let me label this with 6.5. Okay, so backward induction, you all know what the backward induction is. We want to assume as an induction hypothesis that this statement here, 6.5, holds for t up to time t plus 1. So we know it holds for capital T, and now we assume that we have shown it for capital T to t plus 1, and obviously we want to show that it holds for t. Right. Okay. So we have here inequality, so we have here inequality. Standard way to show an equality is we show that we have two inequalities. So let me start with the first slide. One. Okay, let's start on the right side as usual. So we start here. So what is this? So this is, we want to understand why the expected utility of the terminal valve of P star, also generated by P star, given that P star is so starts with a capital X at time little t is equal to this operator TT J t plus 1 X. Okay, easy. And then equal to JT plus 1. So let's use the tower property. These are all tricks we have seen several times in this course. This may be a bit nasty with the definition, but actually the calculations are not super hard. No. Right. No. So the usual trick, we just sneak in another conditional expectation. Okay. But this is nice because, well, what is this here? This is nothing else than jt plus 1 of the applied to the wealth generated by p star at time t plus 1, given as before that at time t we start trading with the capital X. Yeah? But if I know that at time t I have the capital X, well, I can use my recursion formula to express the wealth at time t plus 1 in terms of X, right? So our recursion formula we use every third line tells us that the capital at time t plus 1 is here, the discounting factor plus the terminal wealth we have at time t, X, is given by, okay, depending on our decision rule, F star multiplied with the taking the scalar product with the returns in the t plus 1 trading period. All right. All right. So what is this in terms of our definitions of the operator T? So this is nothing else than TF as a capital T at time T with the decision rule F star T of J T plus 1 given the capital X. And since this here is maximizer in this one period, we know this is nothing else than T at time T of J T plus 1 of X. Right. That's what. And now we take the supremum of all decision rules, taking supremum over F. Well, what do we get? Well, we take here the supremum of F, so we get J at time T. And here, well, this is independent of F, so this stays the same. So TT JT plus 1 of X. Okay. So, well, this is what do we have here? Right. So we have seen now this, and this is easy. All right. So let's do the second, I mean the inverse. Direction. So let's take any decision rule. Call it P, and P depends on our so this is actually investment policy. we'll see, sorry. Investment policy consists of decision rules F, T. Well, what do we get? So let's start here. U, V, I, T. So this is our investment policy P pi as we choose, and then if we assume that we start here at the time t with the capital X, what do we get? Well, let's use the tower property. So we sneak in another conditional expectation of, so we conditioned on capital T, and we conditioned on the wealth we have at time t plus 1, and then we condition as before on assuming that at time t we start with the capital X. Okay. So this can be estimated from above by taking here the supremum of the, so we have the monotonicity of the conditional expectation operator. So we can take our j t plus 1 at time tvt, given as before, we start at time t with the capital X. All right. Okay, what do we have? Right, we can express this v, the capital at time t plus 1 again in terms of our recursion formula. Right, so then in terms of the capital at time x, so what do we get? We have discounting factor time t plus 1, well, multiplied with the capital we start with, so this is your x. And then, of course, it depends on our decision rule, how we invest in the market at time t. And what we have at time t plus 1 is then determined by the returns appearing on the market. And here, in terms of the discounted returns, x tilde. Okay, cool. And what this is in terms of our operators, well, this is capital T at time t, given the decision rule. What is this? Actually, T. Sorry. Yeah, and the decision rule ft, j plus 1. Right. Given x, and this is what can be estimated from above by taking the supremum here. So the overall decision rules. So we have here capital T at time t of j t plus 1 given x. Okay. And now we take another time the supremum of all decision rules, means taking the supremum over all f. What do we get? Well, this is then j t, right? If you take here the supremum. And here, well, this is independent. So we get f capital T, so this stays the same at time gt plus 1. So combining 1 and 2, we have also for time t that jt is equal to capital T at time t of jt plus 1, which is exactly the recursion formula we wanted to prove. So we are done here with our idea, like implementing the idea of the dynamic programming principle, that we indeed can solve the global optimization problem by breaking it down to one-step optimization problems, which we are already able to solve. Okay. Well, let me give you one mathematical, not super interesting, but economically speaking, rather interesting example. Another example, a lemma, which is basically a corollary of what we have done. So what I want to discuss, I want to consider a super simple case as before. The setting is as before, but we want to assume that the discounted returns are 0. So what does mathematically speaking means? This means if I make this assumption on my underlying market, means that the discounted the price evolution of the risky asset is a martingale under the physical measure P. So our portfolio optimization were always considered under the physical measure P. Or you could also understand this as saying, okay, what happens if I start looking at my portfolio optimization under the risk neutral measure Q, or the martingale measure Q? Right, this is actually not what you want to do, right? You really want to maximize the gains and not using this artificial measure, which is the natural one for pricing and hedging. So let's assume the market is really like a fair game, namely it's a martingale under the measure P, in this sense that the discounted price process is a martingale. So how would you invest if you know this? And keep in mind that we have a utility function, which is, captured the idea that we are risk averse. So we have this strictly concavity assumption. So we are a risk averse investor investing in a market which is basically a fair game. So what is our expected optimal investment policy? Well, if I cannot do better than the bank account, because in average I'm making 0 profit, and if I invest in the risky asset, well, I put all my money into the risk-free asset, because there I know for sure how much money I make. And this is actually what we also get out from our theory here. So if in average the risky assets are performing equally well than the risk-free asset, well, I put all my money into the risk-free one, meaning I take all the position to be 0. T-1 is the investment policy for P. Yeah. Okay. I mean, this intuitively makes rather sense. And now we can also prove it mathematically. So I basically need to make what I verbally explained now mathematically rigorous in the proof. So let's do this. How do I do this? Okay. So let me take any investment policy. P star, P, so any means not the optimal one. The discounted value process so capital process here. Is a martingale. Okay, now I have to prove it because we do here proof and not only verbal explanation. So how do we see this? So let me look at the discounted value process here and condition this the discounted value process at time t plus 1. I discounted the condition at the filtration at time t, and now I want to show that this is the discounted value process at time t. This is what I have to show if I want that this is a martingale. So let's do this. And I hope no one is surprised now if I use, why is there a bracket around it? No, anyway. If I use my recursion formula. So this is so the Wolff process at time t plus 1 is given by the Wolff process at time t plus the, well, my decision rule depends on the capital I have at time t. And well, then my returns, discounted returns, determine how much money I have at time t plus 1. And now I still have to condition everything on ft. Okay. So okay, the first part, I mean, these two, this product here, or quotient here, is, oh, sorry, is ft measurable. So I have here, right? And now this is deterministic, so I can pull it out. This is ft measurable, so I can pull it out. So I have here, and this is independent by the independence assumption. So I have here exactly the, there's no 0 because I assume that ft tilde, sorry, f, and the expected value of the discounted returns at time t plus 1 are 0. Okay, so that's exactly what I wanted to have, right? Telling me that it's the discounted value process associated to the investment strategy pi is indeed a martingale. Now I can plug it in the whole theory to see that my optimal investment strategy is 0, but I can also make here a simpler proof by using Jensen's inequality. So what does Jensen's inequality tells me? Well, if I have this optimization, this is my target function, so I want to maximize the expected utility of my terminal. Well, if I follow investment policy pi, given that I have at time 0 the capital X. Well, now this is where I use Jensen, right? So I can pull out my utility function to find an upper bound of this quantity, and this depends on t. Right, so now I want to have my discounted value process there in there, so I divide by t, bt, then I multiply it with bt, and this is now a martingale, so this is just x0, so I have here x0 multiplied with bt. Okay. So what you see here, if we invest all into the risk-free asset, e.g. I choose all the f stars to be 0 for all t from 0 up to time t minus 1. We actually get that this upper bound is attended, so we get that f. So we know there is an upper bound given by I invest all my money into the risk-free asset. This is what Jensen's inequality tells me. And then, okay, well, if this upper bound is attended if I put all my money into the risk-free asset. Okay, cool. I mean, this, as I said, reflects the idea that we have a risk-averse investor who prefers to take the certain payoff created by the risk-free asset rather than a random payoff, which in average gives the same. All right. Okay. Okay. This. I mean, we studied now the idea of how to find or select an optimal investment strategy based on the idea that we have an investor with preferences described by a utility function. There are, of course, alternative ways to find an optimal investment, and one big alternative idea, so which was used, is based on modern portfolio theory, which I also want to briefly discuss here, because we have all the mathematics developed to solve this as well. And this is based on the mean variance analysis going back to Markovich. Portfolio optimization. Okay. Okay, so if you want to look it up or read, do some further reading, or initiate it is probably the right word by now, because I mean, this is 70 years old, or okay, a bit less, 60 years old, and of course many researchers have contributed to these ideas. So this goes back to Marco. It's and since we are mathematicians here, this was not, so there are some earlier works actually in this direction by the mathematician Definetti. Bruno Definetti. But as is often is the case, well, there are different communities using different language, right? We use here our mathematical language to describe similar objects than economists do. So there are sometimes ideas developed in these different communities, and they are not well communicated. So, so these works are certainly independent. But I mean, just to give some credit to earlier works as well. All right. So what was the idea? So, I mean, so far we understood optimal investment in the sense that we wanted to maximize some utility function. So now there's no utility function. Actually, we want to give us a target mean we want to generate by trading in the market. And then we want to do it again in a risk-averse way by saying we want to minimize the variance of our capital, of our investment. Right. So this is, I mean, this is the same idea as the utility function. Reflect risk-averse investor. We understand now a risk-averse investor in the sense that she wants to minimize the variance of her terminal wealth. Okay, so let me introduce the market. To make our life again a bit easier, we consider a one-period model. But you can also always, in this context, you can always understand a one-period model as buy and hold strategies. So you can also say, look, I mean, this is, I mean, not the world is a one-period model. It's not a simple idea, but it's just, okay, I want to decide how I split up today my capital, and then I keep it like this until I retire. And then you have a one-step model, right? What we allow for de-risky assets. So as before, so this is our market. You have seen now several times. Right? And as we use it now, so let me recall the idea of returns. So are defined by RK, and here's no time. So this is RK1, which we define to be, we drop the 1 because there's only one trading period. Right, so these are the returns you have in the risky asset. So this is not the discounted one, these are the undiscounted ones. So K is, of course, for each of these de-risky assets, you can write down the returns. Right. And now let me make some assumptions. Because you see, I mean, if you want to really solve some portfolio optimization problems, you need to assume more than just to have an arbitrage-free market. Like before, we have assumed that it's we have independent returns, and here we want that the returns have a finite mean. So assume that K, which is defined to be the return, the expected value of the kth return, right? And well, What else? We want also to have, we want that the covariance between the returns exist. Kj from 1 to d. Okay. And well, okay, what this is, they exist and are known. I mean, this is what we always assume, that we have the parameters of our model. Of course, in reality, one needs to estimate from real data, one needs to estimate the coefficients of these models. But here, I mean, we develop the math, so we assume that we know these parameters. Okay, and furthermore, I want to, I mean, if you have a finite market, as we would usually consider in this course, I mean, this is always true. So this is actually not a resum. I mean, you could also say, okay, we have a finite market. All right. We assume that we have a market which is basically non-redundant. So if we look at the vector of all the means for returns and the vector E, so this was the vector with only ones as an entrance, they are linearly independent. So yeah, for this section, we need a bit of linear algebra. And we assume that the matrix of covariance, so matrix consisting of these sigma kj, so this covariance matrix is positive definite. Okay, for those of you who have taken linear algebra a while ago, so this just means if you take any vector x and you multiply the transpose with sigma, then with x again, you have something which is strictly positive for all x, except of course if you take 0. So this is I mean, this sounds a bit technical, but basically what I want to say here is that we have a non-redundant market in the sense that there's no asset on the market which can be represented as linear combination of the other assets. Because this would destroy some of our analysis, because basically if you buy this linear combination of all the other assets, this is not a new asset, right? This is then, you could generate it by trading in the market. So you want to clean up your market in the sense that you only have the essential assets to trade in. Well, so yeah, makes sense. Because otherwise you can fool yourself and create risk. I mean, if you have 3 assets and you say, okay, I do some diversification and invest in all 3, but this is actually only 1 because the other 2 are just linear scaling of the first one, you have not created any diversification, which actually is something one needs to be careful about when investing in the market. Anyway, so what's so what we want to do here now? So given, as usual, we have initial capital. X0. Investor, so we have our investor. And investor. And this investor aims to invest x0 into the de-risky assets. So one can also include the risk-free asset in this analysis, but what we say is, okay, we have already decided how much capital we want to invest in our stock market, and now the task is actually to decide how we split up our initial capital in these de-risky assets. Okay. So what is any trading strategy? So we have here this one period model. So the trading strategies. Well, these are phi. So we have a vector. So beta denote the amount we have in the risky assets and the risk-free asset, and my d alphas, they denote this. So these are so here the trading strategies are just real numbers. This is as before. Okay, so this is clear. So what is the budget constraint we have? So our budget constraint or initial capital we have is, since we only care about investing into the amount x0 into the risky assets, so we only care here about the alpha, which is, well, we have the amount alpha as usual, k into the k asset invested, we have k assets, and so the sum of all our position in the market, I mean, the value we have at time 0 should be x0. This is the capital we have. And the terminal wealth, right? So what do we have at time 1? Well, clearly, well, we have our position, we have done nothing up to time t equal 1. So this is alpha k, and the prices involved. So the capital we have depends now on our position in the market and, well, what the prices are at time 1. Okay. Wait. So this is, so what is now the return of, so return of the investment alpha? If we have, I mean, we have invested it into the market, so so in the de-risky assets. So the return is what defined as usual. So consider the wealth we have by trading the market with respect to alpha at time 1 divided by 0 and minus 1. So this is how we always define returns. So let's calculate this to understand what it actually is. Okay, so we have here the definition. This is just x0, right? So if you, I mean, this quotient can be easily calculated by taking the definition of the value processed at time 1. So this is alpha k multiplied with sk1. And here, this is just 0. So this is x0. Okay. Okay, now I have this 1, and I want to have a nicer expression of it. So let me take this 1, I mean, I divide it and multiply it with x0. And now I know by my budget constraint, x0 is also equal to my positions, so the wealth I have at time 0. Right. Okay. And this is not magic. This is just plugging in the definitions we just made, the assumption we just made. So what do we have here? This is okay. Let's make one sum out of it. Okay, one sum. This is nice. So we have here alpha k divided by x0. This is here and here. And then we have, okay, and then we have k. So let's pull out the S0 as well. Means we have here sk0, and then we have here -1. -1. And why do I like this? Because what is this? This is just the return. So this term here, the bracket are just the returns of the risky assets. So what do we see here? Alpha 0. So this is just some real number multiplied with the returns. Okay. So let me make the following definition. So pi is my portfolio. As before, I mean, this stands for the investment decision we make. Consists of D entrance. So this is the investment decision we make for each of the risky assets. And now we have here alpha 1 as 0, 0. So what we do is we call this here, we need to change the color. So many here. We call this pi 1. That's it. But long story short, so short story long means I have here a vector alpha d as d0 x0. So why do I like this definition? Because we get that our budget constraint is now just the scalar product of P multiplied with E. So these are equal to 1. So this is our budget constraint. And the return, here of our investment, when this is defined as above. So this is it's nothing else than the sum here of the PK multiplied with the returns of the risky asset. Right, so, okay, as before, well, this is what surprised you. So here, pi is called portfolio. And R pi is called return of the portfolio pi. Right, so this is, as I mean, consistent with what we have seen before. So this is all right. Okay. A little bit of time. Okay, so what we want to understand is now we want to make a mean variance analysis of trading in the market. So what is the mean? What's going on? we get. So if I look at the mean of my portfolio M, so this means the mean of the returns. So these are the average over all returns. So the expected returns I have if I invest with respect to pi. Right? So that's pi. So what is this? Well, so the pi, or anyway, they are just constant. So I can plug them out. And then I have here with the linearity of the expected the expected value operator, I get mk. Right. So these are the expected values of the returns of the case risky asset. So this is nice. So what we have here is just the scalar product between my investment decisions, so my portfolio pi and the expected returns I have on the market, and we assume to be known, right? So this is here in the orange part, which tells me, okay, I have the expected returns. Okay, that's cool. And what can we say about the variance? Okay, I need to label this for later use, probably. So what can we say about the variance if we invest here with respect to pi? So this is my variance of the returns of pi. Well, okay, I just have to calculate it. So I get here these nice double sum. Of pi, okay, and then I get the return, the variance of the returns of the risky assets. Okay, so this is nothing else than I take the transpose of my portfolio multiplied with the matrix capturing the covariances, and then I multiply with p. Right, that's nice. And here you see actually why I want to have a positive definite matrix. Okay, so what is now when we formulate the criterion we want to do? I mean, there are different ways to formulate it, but these analyses, they all have similar goals here. So mean variant criteria. So this is actually, so what we aim is, and we will solve it next time. So for choosing expected return. So what we do is, okay, we have our target. So we want to generate so we fix the level of expected return we want to generate. And then we want to find actually the portfolio which gives us these expected MP. We want to find the portfolio which generates us this expected return with the minimal variance. We want to select the portfolio pi with the expected returns given by P such that the corresponding variance here M pi is minimal among all portfolios with mean return MP. Oh. Okay. And this is how it's. Oh. Yeah. Okay. So this is how it's formulated in verbally and economically, the economic idea behind it, and now we can formulate it into a mathematical problem in this setting we have. Right. So of course the mathematical rigorous formulation of this idea depends on the underlying model, right? We first need to transfer the real world into a mathematical model, and then we can start calculating on understanding things. So what do we have? So given this level MP, we want to solve the following problem. To solve, so let me call it P hat now, because it's a new optimization problem. So we want to find the minimum over all pi in RD, which minimizes the variance, and the variance here is just given by this formula. So, and okay, let me introduce here just a factor 1/2 to have a nicer proof in the end. Because what we see here, well, what is this? This is a quadratic optimization problem. Such that, well, what are my constraints? So pi, so I want to trade in a market which generates these given level of expected returns. So my pi, the scalar product with the returns on the markets have to match this level. And well, I still have my budget constraint, so I cannot spend more money than I have. So pi multiplied with E has to be 1. Okay, so that's it. So these lines, mean variance criterion is, mathematically speaking, just a quadratic optimization problem with linear constraints. So we can solve it, and we will do this in the next lecture. So you know what to do. You can also go ahead and write down the Lagrange multiplier and solve these 3 equations you will get to find a Kushner-Karun-Tucker point, and then you know what's the optimal solution is. All right. Well, let me stop here and not run into the proof actually how to solve this. Well, thanks for watching.